Okay. So this is problem 3, I think.
Yeah.
Problem 3. Right. Problem 3. Midterm 3. So here is a hint. Just this. U cube is equal to 1. First show that this is equal to 1. Okay. So this first step. So step 1. And that's sufficient. With step 2, I can tell that once you have this, I have discussed them in one of the lectures.
Okay.
Somewhere when we was doing eigenvalues or eigenvectors, I said what happens, how do you find eigenvalues when you're given an equation like this? Okay, I think I don't know, Cayley, Hamilton, spell checks. Theorem or relation, Hamilton's theorem. So first show this, then try to connect it with whatever this theorem is. And I discussed this in the lecture for maybe 2-3 minutes, or maybe 1 minute or something. So if you really can scan through, it's hard to go through 5 hours of lectures and say 1 minute on there. There is a solution. So hopefully that helps. Okay.
Yeah, definitely. Thank you, brother.
Yeah. Okay. Otherwise, it is okay. Going fine. Other problems. What about the last problem?
I am working on it actually.
Okay. But do you know how to proceed?
I think so.
Okay. That's sufficient. Yeah. Good. Okay. Is there any homework due, or we have finished all of them?
No, we are done.
But is there a homework due? When is it due? Is there a homework due?
No, any.
No homework.
Yeah.
No. So there's a midterm exam that is due tomorrow.
Yeah.
So I can give one homework, that means?
Yeah,
Right?
I think
On-
so. This is
Yes. So there will be a homework. Which homework is this, by the way?
this is 9. It's 9.
Probably homework 9.
Yeah.
Right? Homework 9. So homework 9. The due date is flexible, but I have to officially say that it's due on Friday. Right? So this is December 3rd. Friday. Right. So late night. That's it. Okay. But it is flexible. You can take your time, but it cannot go beyond final exam. Right?
Yes.
When is the final exam is on? The final exam is time, I guess. When is your ENM exam?
No idea about it. I didn't know.
But officially, when it is, there is an official date. You guys know that, if you go to SIU webpage and search for SIU final exam schedule, so final exams are scheduled at a certain time, and typically instructors do not change it. It's very, very rare, it's under very special cases, and the students are approved that. So this is not my choice. So decided by the university, right? And it is based on when the class meets. We meet at Monday and Friday at 9:30. That decides where the exam is. So you guys are meeting right after this class, so that will decide when the exam is. Okay. Yeah. So there's 2 things due. And so here is how I'm thinking how the final exam should be. So there will be about, let's say, 60 to 70% of the final exam will be a take-home part, like so that I can cover whatever I'm doing now. So it will be a homework, it will be like a homework. But 40% we will have whatever we are telling. There will be a, I will ask something from the homework, like homework, small step. Is that clear? So I think while I was thinking, I think that's something that I might do.
So there will be a deadline for the take-home part.
Yes. So let's say, let me make this clear. Okay. So the take-home part will be available. Let's say final exam will have two pieces. Let's say 60%. This distribution I'm not very sure. Okay, and 40%. Right. 60% will be take-home, which will be available. Let's say today, like right when I make the homework, it will be an extension of the homework session. But it will be due on the day of the exam. So you write the 60% of the exam and bring it to the exam, right? It's take home in the sense you work at home, but it is due or you bring it. So it will be considered as an exam, part of the exam. So 60% will be graded as a homework kind of stuff. And 40% based on details of homework of midterm. By details, I mean when you have steps going from A to B in a homework question, which is taken for granted, I can question that, or I'll try to confuse you guys as to, oh, is that really true, right? Something like that. So I think that then it will be less stressful, I suppose. Right? So you know what to expect in this. You'll be able to, and you can talk to each other outside this. 60%, you can talk to each other, students, and even me. You can come back. This thing we will make it very, let's say 4 questions, small 4 questions. That will be 2-hour exam, but very simple 4 questions. It should be possible to do it very quickly if you know it. Typically, everyone struggles with these kind of questions, so it can be challenging, right? Reasonable. So that will give you a. So basically, take the homework and try to scan it through and question it. Why did I do this? Why did I do that? Right? What can imagine what I could ask? Okay. Yeah, so we want to do angular momentum. So we did harmonic oscillator, and the next very nice construction one can have in quantum mechanics is angular momentum in the spirit that we are trying to do. So you notice that I hope you have done quantum mechanics in a spirit where you start from Schrodinger equation and get eigenvalues, eigenfunctions. That's great. That really helps a lot to connect with physical systems. Here we are trying to get the symbolic form of quantum mechanics, where we try not to solve a differential equation. We try to get the algebra of the system. For example, harmonic oscillator, just having the commutation relation told us a lot about its eigenvalue, right? Eigenvalue, eigenfunctions, and we could even solve for differential equations if we want to. But almost everything was there just the moment you gave a Hamiltonian and a commutation relation. Same thing we want to do with angular momentum. It is much more richer. There are 3 operators now, Lx, Ly, and Lz. And in all this discussion, we will stick to orbital angular momentum if you want. Or the early part when I'm working on it, it will be any angular momentum, whether it's spin or orbital. But let's say the thing I'm thinking of giving as a exam, that part will be orbital angular momentum. It will not talk about spin, so there will be a restriction of that. How do we see angular momentum? We will think of it as rotations. It's very closely related to rotation. So the question arises: how is it related to rotations? Why is it related to rotation?
The name also says something angular. That means there is to have some angle.
Angle, yeah, reasonable angular momentum, yeah. But let's say, how about this? Angular momentum is related to angles, correct?
Yeah.
In that spirit, what is energy related?
Angular velocity.
No. So the question is, so that is angular momentum, right? And then you say that think of a conservation of angular momentum. If angular momentum is conserved, can you think of a system where the angular momentum is conserved?
In a wheel, in the car wheel, angular momentum is conserved.
Circular path movement.
Circular path
Movement like centroids in this projecting towards the center. Circular movement.
Circular movement, and tell me again. You mean
Like anything.
Anything that is going in a circle?
Circular.
What if it is on this table? Something going in a circle, is the angular momentum conserved?
Not always.
No.
Right? Because there will be a torque due to
Yeah.
gravity. If there is a torque, then the angular momentum is not conserved, right? So remember that dl by dt, right? So this is angular momentum, right? That's classical mechanics. That's equal to torque, right? Or due to first force, torque due to second force, right? And if I'm saying that angular momentum is conserved, that means this should be zero. So that means all the torque should be zero. Yeah, something going in a circle, typically we think of it as angular momentum is conserved only if the torque is acting right on the axis itself, so that somehow this should all be equal to zero. So that's a good thought you're having. But suppose we need an example of of an angular momentum being conserved. Best is to have torques all equal to zero, right? And if you don't have any force, that's something where angular momentum is conserved. So you take something going in a circle, let's say an atom, right? An atom electron is going around a proton, right? So the electron's angular momentum, so there is an angular momentum associated with this. But now if there is a gravity acting, this is not conserved, right? Because gravity will try to rotate this around. But if you were in space, then there is no torques, right? So the angular momentum is going to stay the same. So if you have an atom where there is a proton and there is an electron going around, it has an angular momentum perpendicular to the plane of rotation. That will stay the same. An atom can move around whatever it wants, but its angular momentum has to stay the same if this equation is true. Is that clear? For example, in our planetary system, if Earth, all the planets are going around the sun, it has an angular momentum. In whatever direction it is pointing, it has to point the same direction all the time because there is no other force acting. Right? To our knowledge, there is no other force acting, and that is true when we measure things with respect to the stars. That axis of rotation remains exactly the same. Right? It can get transferred from the electron to proton, or in this case, planets to sun, but overall angular momentum has to be the same. So that's Correct. But now let's say that if the angular momentum is conserved, so yeah, so you have this axis, so there is an electron that's going around, and now you look in this direction or in this direction. Will there be a difference? Like, think of our planetary motion, right? So maybe you can draw this, right? So that is the sun, right? And let's make this circle. So this is a, let's say Jupiter is the only planet, let's say Jupiter is pretty heavy, and this is the most dominant one. So let's say nothing else is there. Now this is going around the planet sun. Is there any difference between this direction or this direction? Like, as far as the sun is concerned, when the Jupiter is here, it has an angular momentum. Here also it has the same angular momentum. Here also it has the same angular momentum. This angle doesn't matter. It can be wherever it wants to, and its angular momentum will be there, as far as it has the same velocity. Right? When you're going in a circle somehow, the information is independent of the angle phi position or the angle phi. So my point is that if this is constant, angular momentum about this axis is constant, that means this angle, there is no dependence on angle phi. Is that clear what I mean?
Yeah.
So what you would mean by that is that if angular momentum is related to phi, which means not only phi, if it is conserved, that means it is independent of phi. So derivative of angular momentum or derivative of any physical system with respect to phi will be zero if the system is having a conservation of angular momentum. Is that clear? Questions?
Phi there means azimuthal angle or normal angle?
I have chosen my angular momentum, so the LZ to be this direction. Okay, so there is an angular momentum in this direction. The angle that is perpendicular. So first find the plane that is perpendicular to that and fix an angle with respect to a line in that. Right? Typically, if I say LZ is this, then this is a azimuthal line, right? Theta is the polar. Is that clear?
Yeah.
Okay. There are three angular momentums, so there will be three angles. So it is not phi 1, so it is not phi, there will be phi 1, and phi 2.
So every momentum has their own orientation.
Their own orientation, right? Lx, Ly, Lz. Right? Angular momentum has three components. So all three will have its own angles, and we will talk about how to, like, we won't use this angle phi 1, phi 2, phi 3. Instead, we will use a better parameterized series. Oh, phi 1, 3. Okay. But my question was not that this is what we want to study. We will talk about angular momentum. But the way, if angular momentum is conserved, it means that there is an angular symmetry, or you can say there is a rotational symmetry. In that spirit, I'm asking if energy is conserved under what is the parameter with respect to which things remain the same. So I'm telling Hamilton or the energy. It is time. Okay? If there is
It doesn't change with time.
it doesn't change with time. If any system, any property doesn't change with time, that means energy is conserved. Like, or everything in the system should not change with time. like if you have like the whole universe, we say that as a whole, quantities are not changing as a whole. Like, and then you say that, okay, if energy is not changing with respect to time, then translation with respect to time should be okay. Like we should not be able to, like whether I'm talking about tomorrow or yesterday should not matter, or for that matter, a billion years ago, I still will have the same energy. Like energy will not change. Yeah. So translation and time implies or symmetry under translation and time. If things do not change in time, then energy is conserved. Is that clear?
Is it same for the macroscopic and microscopic system?
Yes, it's the same. It's completely same, because what we do is that if by I think you don't mean microscopic, you mean delta t, right? Infinitesimal change in time.
Yeah.
So we prove these things for infinitesimal time, but if it is true for infinitesimal, you can keep adding it. Especially in time, they are commutative, so you can keep adding on. Rotations is slightly different in the sense that you might have rotations, a rotational symmetry in one direction, rotational symmetry in the other direction, but these two may not commute. You first do this, then you rotate in that direction. That may not be the same as going this and the other way. So rotation can give non-trivial features even if it is conserved. That's what we will see. But most of, especially one-dimensional time, like you go from T1 to T2, T2 to T3, that's the same as going from T1 to T3 and then T3 to T2. It's like it's commutes. That's the best way. So energy is related to time. What about linear momentum?
Force?
No, because here it was not thought, right? Like this.
Oh yeah, there's no problem.
Yeah. Here it is position, right? If things do not, like if I were to, like the way you say it is that I have this room and while you guys are sleeping, I move this room by about 10 meters, but I move everything in this room, right? The tube lights, me, everything on the floor, whatever forces are acting on this, everything is moved by 10 meters. And the question is, will you be able to tell the difference? Can you make an experiment and tell, or did I make a move of 10 meters? Can you test that move? Okay. So the question is, if you can test it, that means linear momentum is not conserved. If you cannot test it, that means linear momentum is conserved. So that's and this is, I'm telling it as a statement, but one can prove this in classical mechanics. This is what is called Noether's theorem, N-O-E-T-H. I think I'm pronouncing it wrong here. Noether's theorem.
I read about this.
Good. Yeah. So that's the statement says. Okay. So this is X, right? So this is time, but this is translation in time. This is translation X. This is rotation, and rotation is angles phi 1, phi 2, phi 3, or you can say think of it as orientations in position. There are three positions, right? So three positions, three angles, one time, and there is one more thing you say. This is let's call it boost, right? So let's call it the boost oscillation. This doesn't have anything. We don't study this in classical mechanics, but the idea is that there is one more operation you can make. If if there is a relative velocity, I move with a velocity 30 meters per second, and you guys are moving with 20 meters per second. And if you go at 30 and I go at 40, relatively speaking, you won't be able to tell whether everything has changed or not.
Yeah.
right? A constant velocity, you cannot make the difference. For example, our Earth is moving around, right? So the question is, can you design an experiment which measures the velocity of Earth going around the sun? And that's very difficult. It's not just difficult, it cannot do it, right? Because it's an inertial frame, you cannot design anything unless you now say that if you're very, how would you test this? If I would ask, have you ever thought of an experiment which measures your movement?
Relative movement.
I can use a device if it is possible.
Yeah, you can use anything. I'm saying any device. We are talking about this is a strong statement. I mean, can you think of any device which will measure the velocity of Earth? Except you cannot go outside. Like, of course, you can go on a satellite these days and, oh, this is moving with respect to the stars. That is possible. But let's say you are sit on Earth. Your experiment has to be on Earth. And see, there's now I have to put in constraints. You cannot use the stars, right? That's all possible to do. It's like saying that if you're in a metro train, a subway train, and if your windows are closed and you're going with constant velocity, can you measure the velocity? Yeah, that's a better experiment. Let's not talk about, let's say you're going in a car and you ask your driver to go at constant speed. Let's say you put it in cruise or something. And imagine you have closed the windows. Like, don't close the windows because then you cannot drive, but imagine the windows are closed. Now design an experiment which can measure the velocity. No interaction with outside.
It's not possible.
Yeah, it's not possible.
But I have to compare relative to something.
Exactly. So that's the essence of what we are talking about. Right, and there's an operator associated with it. So every parameter, when you do this, there is a connection you make with an operator. So that's called a boost operator. Okay. So this, let's say, is velocity. So this is V1, V2, V3. Notice that there's three angles. Typically, we say this is omega, this is time, this is position vector, and this is velocity. So this is 3 plus 3, 6, plus 1, 7, plus 3, 10. So these are called, this whole thing together is called a Poincare transformation. Okay. But let's stick to this. Like, in the limited time that we have, we took up this project of doing things in quantum mechanics. Well, let's in the limited time, let's just do angular momentum. Angular momentum, we're talking about rotation. So we want to ask about how do we define a general rotation in three-dimensional space. How we are going to define rotation is, so this rotation, any rotation will be, we will see, is equal to, first there is an axis, right? Instead of saying that, okay, there are three rotations possible, about three angles, so you need three parameters. Instead, what you do is that there is an axis, so this is a direction, right? So there is so first you decide what is an axis. Any rotation can be imagined to be a single rotation about an axis. Okay, so first we have to get which axis is this, and you make an angle that we rotate, right? So you would say omega is equal to omega 1, omega 2, omega 3, right? So that's a vector. So what are these vectors? Omega has a direction, right? Omega hat. This represents the axis. Okay. And the magnitude, which is omega, is the angle of rotation. This is omega hat. So there is a direction and there is a magnitude is given by that. Is that clear? So how I defined that?
One question. So W hat is axis. Is it? I mean, you choose it as axis or?
I choose this. So I'm going to show that rotations can be written in terms of this parameter alone. And then I'm defining what do I mean by this parameter, and I'll show what is W1, W2, W3 very quickly. But what we want to see this is that any rotation, like let's say, for example, a simple rotation would be, I have a sheet of paper, I rotate it by 90 degrees. So let's say that's z-axis, right? So I rotate it about z-axis by 90 degrees. And then let's say this is my x-axis, I rotate it about by x-axis. So there is two rotations I made. But the claim is, what I'm saying is that this two rotations can be achieved by a single rotation about an axis, which doesn't have to be x, y, z. So pick one axis and an angle, and you can get the same rotation and however you got it, right?
Yeah.
And that parameterization will be that the direction will be given by the direction of this vector, and the magnitude, how much you have to rotate about that angle, will be given by that magnitude of it. Okay, but of course, this is not very obvious that every rotation can be written this way. So we go back to, let's say there are 3 rotations, right? We do know that any rotations can be achieved in terms of 3 rotations. That's much more easy to see. So let's think of rotations about an axis, about x-axis, right? So rotation about, let's say, z-axis. So that's will be x prime, y prime, z prime. Okay, that's the transformation. And I'm rotating. So this is my x-axis. That's your y-axis. So that's your 2 coordinates. So let's say this is your ij, right? Let me put it like that. So this is your x, comma y. If I were to rotate this, but by an angle. So now I have to specify an angle. So let's say this is omega 1. Right. So if I were to rotate it by an angle omega 1, so this is my z-axis. So this will be cosine of omega 1. And then there is say minus of sine omega 1, sine of omega 1, cosine omega 1, 0, 0, 1. Is that clear? One can derive this just by using coordinates, right? So suppose this is your x, that's your y. Now you want the coordinates in terms of this, right? This is your x prime if you want, right? And y prime would be like this. This distance is your y prime. This rectangle is what it is. But you have to go back to your x and y, so you can use coordinate geometry to get that, right? So we have done this somewhere else, so I'm not going to do that. So is that acceptable?
Yeah.
Okay, we can begin. with that. Okay. But we want to work with infinite. There is a lot of advantage you can get by talking about infinitely small. This angle need not be a large angle, make it infinitely tiny angle. And then we can make approximation, right? Sine of that angle is really tiny, cosine is pretty much 1. And that is, and then we can add up. If you want to make it big, then you just have to integrate that on that. Okay, so let's split. So let's quickly do that. Okay, so this makes this. So this is x prime, y prime, z prime. We are telling that omega 1 is small. In fact, what I say is that first say omega 1 is small. So basically think of omega 1 as delta omega 1. Just because it is small, I'm going to write omega 1 as delta. So notice it's not a change in omega 1. I'm replacing omega 1 with delta omega 1. Right? So in this case, so this becomes 1. And this becomes minus delta omega 1. Right? So in this case, sine of omega 1, you first switch it to sine of delta omega 1, which is equal to 1 minus delta omega. Right? Sine of the angle is delta theta itself. Sorry. Plus higher orders in omega. Next one will be omega cube, right? So we drop that. Same thing with cosine omega 1. First replace omega 1 to delta omega 1 just to specify that we are thinking of small angles. And this will be 1 minus delta omega 1 square over 2. But I don't want to keep square, so I'm just going to say 1. It is 1 minus higher orders. Clear? So that makes this 0. That's delta omega 1. This is 1, 0. Let me make sure my notations are correct. Have them at all. We'll see. There's a chance that I might switch this minus to here, like it's a matter of notation. For now, let's keep this. Okay, so that's good. So this is x prime, y prime, z prime. Write this as 1, 0, 0, 0, 1, 0, 0, 0, 1. That's straightforward. But then this next piece, I will write that as yeah. So this is 0 minus omega 1, 0 delta omega 1, 0, 0. Right. And let me not write x, y, z. Change the notation actually. So this is x1 prime, x2 prime, x3 prime. This is x1, x2, x3, this is x1. With me? Yeah. This is x1, x2, x3 itself. This is identity times this. So now let me have a notation, or actually, let's do one more step. Yeah.
This step, last step is from the upper step.
From the upper step itself, I wrote this as 1 plus this, 1 plus this matrix, right? First matrix multiplies this, second matrix multiplies this. So, still confused. Asking again. Like this matrix can be written as this plus this.
Yeah, got it.
Correct?
Yeah.
Is that okay? So I can write this as x1 prime, x2 prime, x3 prime. This is a vector now. This is x1, x2, x3. We're making a small change. We are asking, we make a small change in the axis. What is the change in the vector, right? So this is plus, right? Or let me write this as minus, right? Minus of delta omega 1 times x2. And the second piece is minus delta omega 1 times x1. And that is 0. Okay. But now I want to make a rotation about about the y-axis. Like if I make a rotation about the y-axis, the same thing, but this one now gets moved to the other one, right? So first I make this, so next one is going to be, so this is about x-axis, next is about y-axis. But I have acted on this. So I start from here and then get back on the other piece, x1 double prime, x2 double prime, x3 double prime is equal to same x1 prime will sit on that, but now I'm doing 1, 0. This is going to be plus delta omega 2. This is 0, 1, 0 minus delta omega 2, 0, 1. And then this is x1 prime, x2 prime, and x3 prime. And we are keep only till the leading order. But this one was already having this matrix, correct? And what will happen is that that's sitting in here, that's still leading order. So overall, if you put in all three together, what I'm trying to say is that I'm actually could have done this better, more organized way. So in general, I'll get x1 prime, x2 prime, and x3 prime, the final one. This will be equal to 1 delta omega 1 minus delta omega 2, no, minus delta omega 1 plus delta omega 2. Is this clear or should I clarify? Actually, jumping is big steps. This is about the first axis. The second axis similarly will have here, and the third axis will have here. Is that clear? No, it's not clear. So let's see. Okay. x1 prime, x2 prime, x3 prime. This should be better. So this is cosine of omega 1. And I said minus, right? Minus of sine omega 1 and sine of omega 1, cosine of omega 1. So that's the first matrix. Second matrix, this is z-axis, let's say x axis. So this is x, right? So 1 cosine of omega omega 3. That's up, right? Messed up. I was doing it about the z-axis. I wanted to call this omega 3. Right? That would have been better. Right. So let me make this omega 3. So sorry about that. notational glitch. So this will be omega 3. Okay. Right. Is that clear? Okay. And this one now, omega 3 means here, this will be omega 3. Let's keep this omega 1 there. Right. About the z-axis, I'm going rotating it by omega 3. Y-axis, I'm rotating by omega 2. X-axis by omega 1. Right. So let's do this in order. So first I do x, y, z. Right. So this is what I'm going to do y. I'm going to do this in the right order. So this is y. So this is cosine omega 2, 0, sine omega 2. 0, 1, 0, and this is minus sine 2, 0, sine omega 2. And finally, x-axis in the 1, cosine omega 1, minus sine omega 1. X-axis. Hopefully, I didn't lose you guys completely.
Now it's better.
Okay, so this is 0, 0, 1. So this is an rotation about the x-axis, right, by an angle omega 1. This is a rotation about the y-axis about an angle omega 2. This is a rotation about the z-axis by an angle omega 3. Notice that I chose this angle to be positive and one of them to be negative. That's just a notation. Right? Always in rotations, we do this, one of them. This has to do with the right-handedness nature, like x, y. When you do x cross y, we get a z, right? So the right-handedness is coming in there, right? That's the only reason. But in principle, it's not neat, but it's standard to do that. Okay. This is finite rotations. Now we want to make it infinitesimal, like infinitely tiny rotations about each one. The same argument as earlier, we replace all this by 1 and all this by minus delta omega 3, right? So I'm going to do that. Okay. So this is 1. This is 1, 0. Okay. I should have gone slow. Now anyway, I got slowed down. I was wanting to go fast and jumping steps, but then I missed. Okay.
Yeah.
So this is, I put an arrow instead of equal to sign because I'm not saying omega 3 has been switched to, so omega I has been switched, has been swapped, right? Delta omega. By I mean 1, 2, 3. Okay. Let me multiply this. Let's go slow now. This is equal now. So this is 1 minus delta omega 3, 0, 1. This one, when I multiply 1, remember I I do not keep higher orders. When I multiply this, by any chance, if I get a second order term, I can drop it. Right? So this is 1 times 1, and this is 0. So this is just 1. This one multiplying by this, that is a delta omega 2 multiplied with this. So that's 0 again. This multiplied by this, that is a delta omega 2. Again, notice that I'm dropping higher order terms. So this is 0, 1, and that's minus delta omega 1, and minus delta omega 2. Delta omega 1, and that's 1. That clear?
Just multiply.
Yeah, that is just multiplication, but I'm dropping it cross. Like for example, this one, there is a cross term.
Del 1, del 2.
Delta omega. Yeah, for example, this, when it multiplies this term, this should be delta omega 2 times delta omega 1. But I'm dropping that, saying it's higher order. Right? It is 2 lead, second order. Like remember, this is first order, right? Second order, I've dropped there. So anyway, I have missed something. What's the point in keeping it there? Because anyway, I won't be able to capture that. This is already lost.
So it is like delta omega 1, delta omega 2. Which one you pick?
Both. Any double thing is dropped. You're saying that it is of the same order.
Okay. So dropping means replacing it 1.
No, dropping with it is 0. For example, what we are saying is that let's say delta omega 1 is 0.003, right? And delta omega 2 could be 0.0007.
Yeah.
Right? Delta omega 1 square will be small.
Mhm.
Even this will be small,
Mhm.
delta omega 1. So we are doing the approximation where all orders of delta omega 1, delta omega 2 is set to 0. Right? Delta omega 1 square is set to 0. And delta omega 2 square is set to 0. Any double orders, we just put it to 0. Okay? And that's the idea of infinitesimal, infinitely kind. Okay, so there's one more we have to multiply, so let's do that. Again, we drop higher orders, right? So this is 1. And this one is minus omega delta omega 3. And this is delta omega 2. That is this term multiplying this term, but that's higher order.
Yeah.
And if we do this, this comes out delta omega 3, 1 minus delta omega 1. That is minus delta omega 2, delta omega 1, and 1. We good?
Yeah.
I can write that as x prime, y prime, z prime. The matrix can be written as an identity matrix plus something, right? Right, so this is 0 minus delta omega 3, delta omega 2, and minus delta omega 1, 0
Delta omega 3.
delta omega 3 minus delta omega 2, delta omega 1, 0 times x. And let me again go back to x1, x2, x3. Right? How would I wrote that there? Okay. this is, I'll write this as x1 prime, x2 prime, x3 prime. That's equal to identity matrix multiplied by this will be the vector itself. So it's x1, x2, x3. And let me write this as delta omega 2 times x3 minus of delta omega 3 times x2. That's the first piece. And next one is, let's say, delta omega 3 times x1 minus delta omega 1 times x3. And this is delta omega 1 times x2 minus delta omega 2 times x1. Correct. There's a pattern in this. Does this ring a bell? In vectors?
It's cross product.
Yeah, it's cross product, correct? Very good, very good. It's a cross product. So if I were to think of this as vectors, right, especially delta omega, so let's me write this delta omega as delta omega 1 in the I hat direction, or instead of like that. Right, that's your three rotations. So if that's a vector, then I can think of this as vector x prime, right? So there was an original vector whose components were x1, x2, and x3, right? This is the vector I get after rotations, infinitely small rotation. But what is that rotation equal to? That's delta omega crossed with the vector itself. So we are able to capture our rotation in terms of any arbitrary rotation in principle, omega 1, omega 2, omega 3, in terms of a single vector. And now this should be imagined as, so this is consisting of this vector, right? Omega 1, omega 2, omega 3, that's a, not a position, it's three angles, right? These are the three angles from the components. But whatever that three angles, that direction, that's the axis. Right? And the magnitude is your single rotation, if you want. That's one way of looking at it, but this is perfectly fine. We just have to imagine that this rotation describes any rotation in general, any infinitely tiny rotation. So for us, rotation means this vector. And what exactly is the transformation? That's got by the cross. Okay. Now, I had originally told you that I might switch at the end, whether this is plus here or minus here, I'm not very sure. Okay. I want to keep this minus, right? So all the signs I want to switch right from the beginning. Okay, that's my bad. I should have started correctly. So switch, right? So at this stage, I think, yeah, switch, right? So notational switch. Is that clear without any confusion?
Yeah.
Right? All the omegas, I'm going to switch to negative and permanently. So you should have gone back and I should have put back all the negatives as positive, right? All the omegas are positive. I don't even have to say delta omega. Omega I is going to be minus omega I. Right? It's just a notational switch once and for all. I won't do this twice. That's so there's no errors. So then my relation is x prime is equal to x minus delta omega crossed with x. When you're doing a calculus kind of quantity, you talk about delta x, and this is my delta x. Right? Under rotations, how did my x change? X minus of a delta x, and that's my delta x. Is that clear? Right, that's just a notation. I can make that, or I don't have to actually. So yeah. Okay. Clear. So I'll stick to this. Yeah. So this is the change in x. Originally there was this x. This is the change in x.
So there should be, I mean, a bracket between that omega and x.
No, right? A cross B, you don't need brackets, right? Oh, you mean this? This way?
Not exactly. You told that x minus del something.
Oh, yeah. So what I meant was that x prime minus x, right? This is defined typically as delta x. If I make a rotation, what is the change in x?
Yeah.
Right? This is the change in x. This will be equal to x prime minus x is equal to minus delta omega cross with x. It depends on x itself. Is that clear? Now, when I make this small change, I can also define this as negative delta x, right? And I'm not specifying that. So that's why I don't want to write it. Because the moment I write it, then typically we say it is plus delta x, but here I'll be doing minus delta x. So let's not talk about it. So this is the change, and this is changes this. I don't define it as anything. This is a change is equal to this. Is that clear what I meant?
I have this question too. So these two are same, identical.
Oh, no. Yeah, so this is, okay, that's what you mean.
Yeah.
So yeah, so this is delta omega is just this. Is that, so the question was that delta of omega crossed with x. Do I mean this or do I mean that? Okay, actually there is no confusion in the following sense. Let's let's see. This is a differential statement. So this is usually comes up in other places also. So, okay. So what we have is, let's say x prime is equal to, I'm making this, so this is my definition. Okay, delta x, where delta x is equal to delta omega crossed with x. And you would say, oh, that's not very clear. Delta is acting only on this. Usually any derivative acts everything on the right, right? So this should be on this also. So let's pretend that that's the case. I meant only this. Okay. But in this case, what happens is that, so let's say that this is equal to delta of omega crossed with x. Right? There's a question mark. Right? If that is the case, this will be equal to the, now it has to act on both, right? Delta omega crossed with x, and so this is just this one, plus omega crossed with delta x. Agree?
Yeah.
And delta x is now equal to, so this is delta omega crossed with x, plus delta x is this. So it is omega crossed with delta omega, right? And again, this is double now, right? This is delta omega crossed with x. Right. So I can put this as a chain now. I can keep going. Delta omega crossed with x plus omega crossed with, again, first one, crossed with x. Plus delta x crossed with delta x. Is that fine? Okay.
Yeah.
And I was thinking that this will be second order. Actually, it's not, right? This is not second order. This is also leading order, right? This could be a finite angle. and you make a small change in angle. This is not what I meant, okay? So yeah, I was thinking this will go to 0, but this doesn't go to 0. So yeah, so there is a notational issue here. So what we should say is that this is what I mean. So this is not what I mean. Okay. So first I said that, okay, this is that, then I was trying to argue that no, it doesn't matter. Even if I do this, this will be second order. But it's not second order, this is leading order. And in this case, if I again put, then there's still, it keeps going, right? So that's not what I mean. So I mean this. Is that clear? Did I answer your question? So delta omega is a single parameter. So delta omega is delta omega 1, delta omega 2, delta omega 3.
Right.
That's exactly what I mean. Okay, so this is all not. We mean this, and it will turn out that most of my notes and homework, I won't put this parenthesis. That means that delta omega is a single piece treated like that. Okay, so that might be a confusion. Yeah, good point. Okay. Okay. Do you guys have a class?
Yeah.
Okay. So yeah. Okay. So the only thing I've done here is today, which it took a long time, is that this is delta omega cross with x. That's it. Right? What I will do next is that we will build rotational transformer. First operation, then again do a rotation. So I want to do 2 rotations. First about one axis, then about another axis, and then I want to undo it. Then I undo this and do this, and you will see that we won't reach the same place. And that's what we want to talk about. Very slow. We have 1 lecture remaining. We will see how it goes.
Thank you, Professor.
Yeah, you're welcome. And the exam things were